your drink right there. How many calories in that thing? 170 calories. Anybody else got some product here other than water? That's going to be 0. How many calories if you drink that whole thing? 125. 125. Okay. Now, that's, I'll tell you in just a moment, that's not quite what I'm giving you here for science. A calorie. This is how its amount of heat, energy needed to change the temperature of 1 gram of water. See, once again, we're using water as our basis, by 1 degree Celsius. Okay, this is how in science a calorie is defined. It's the amount of heat needed to change 1 gram of water by 1 degree Celsius. Let's think of a picture of that. I've got a teaspoon. Okay, a gram of water. Can anybody tell me how many milliliters that's going to be? You know the density. How many milliliters is that? No, I don't have a whole teaspoon. I have 1 gram of water. Let me clarify. I've got 1 gram of water. How many mils? Just 1. I got 1 milliliter. And a milliliter is 1/5 of a teaspoon. Okay, so I got this teaspoon with 1 milliliter of water in it, a really tiny amount. And I have a little birthday candle under the spoon. Okay, I'm heating it up with it. I have a baby thermometer in there. Okay? When it changes that water by 1 degree Celsius, that was a calorie. So a calorie is a really small amount. Okay, now, when they talk nutrition, so if you're going into nutrition or dietetics or anything like that, what it says on here is kind of a lie. And historically, here's what's happened. When food people talk calories, they're really talking kilocalories. Okay, so we've gone through some transition. But way back, when I first started teaching chemistry, the food people were saying it's, what'd you say, 120? 170. 170, and they'd say big calories, because they thought we were too stupid to understand kilocalories. And they still don't want to use that nasty metric-sounding phrase. And so what do they do now? They put this on here, but if you look, they always capitalize calorie. And that indicates what they really mean is kilocalories. But you know, everything's relative, so it doesn't really matter when you're talking about how many calories you can have for the day and not gain weight. So they're talking actually kilocalories, but these are actually kilocalories, so it doesn't make any difference. But I just wanted you to be aware that they're using the term a little bit differently than we do. Okay, historically, we in chemistry loved the calories, and we worked all of our problems in calories. Down the hall, and universally, physics folks talked another unit called the joule. And its joule is spelled like that to honor somebody. It's not jewel like jewelry. Okay, so 1 calorie, and you don't need to remember this. 1 calorie is 4.18 joules. Okay, so a joule is even smaller. So there was discussion, and the physicists twisted our arms, and they go, let's all do it the same. And so we caved, and so we do all of our heat problems in joules. Now, if you go on and take organic chemistry, the few heat problems they talk about, they still are using calories and kilocalories. But in this class, we're going to use joules. And the next part of that idea we have a constant for every substance called the specific heat of the substance. And do not confuse that. Specific gravity, specific heat, they're totally different things. Specific heat for water in the liquid state is 4.18 let's analyze what that means. And this is a number I will provide to you. Okay, if you have water in the gaseous state, it's actually some number, 2.03 joules per gram per degree Celsius. Every substance has its own specific heat. Would that be a physical property or a chemical property of that stuff? Now, we're not burning it or anything. All we're doing is warming it up. If it's physical, because you can measure that without destroying your stuff. You're not doing a phase change here. You're just warming it up. Okay. Every substance has its own specific heat, and not just every substance, but the phase that it's in. It makes a difference, because I think one day I showed pictures here, like a gas, the particles of a gas, widely separated where a liquid's closer together. So, those are different. Now let's take a problem to illustrate a heat problem. And I'm skipping over 117. Take a look at that for next time, and I'll try to start the hour with it, but let's jump ahead to 120 right now.